Text, engineering.indeed.com. At Indeed Eng. Tech Talks on the fourth Wednesday of every month. How to get a job 35 million times a day using RabbitMQ, Keaton Gangatirkar and Cameron Davison. Mr. Gangatirkar speaks before a crowd with a slide presentation projected on the wall behind him.
As Doug said, I'm the development manager for the aggregation development team.
Web page shows job search results for Java.
Here at Indeed, our flagship product is job search. Job seekers give us keywords and/or a location, and we return matching jobs. You'll see two types of results here, sponsored and organic. Sponsored and organic have the same job content, but we get paid if the job seeker clicks on the sponsored job. That's our business model.
Next slide, text, aggregation gets jobs. Company logos, including Tesco, Philips, and Unilever.
Some jobs do come directly to us, but they are the exception. By and large, we need to go out and get jobs. Aggregation is the system that interacts with employer, recruiter, job board, and staffing agency sites to get jobs into our search index so we can deliver them to job seekers. We discover them, we extract them, and we pass them down. Sorry, I had a bit too much salsa. Aggregation is not spidering. Spidering means you look at the web as web pages. Aggregation looks at job sites and sees jobs.
How spiders see job sites. Several boxes labeled page interconnected by arrows.
This is how a spider might see a website.
How Indeed sees job sites. A flow chart that has a start box at the top which leads to two navigation boxes, then job lists, then jobs.
This is how Indeed sees websites. We see jobs. We understand that these job sites have structure to them. We know how to navigate through that structure to get the jobs and only the jobs. Aggregation, again, is not spidering. There's structure, as you just saw. There are semantics to the job navigation pages and to the job detail pages. And navigation can be about more than just following links from one page to another.
SoftwareSalesJobs.com. Search jobs page.
Take this job site that we aggregate. A traditional crawler can't get to the jobs from here because you need to post something. You can't just get a link. The aggregation engine is able to do a post from this form with the right data and continue on to the job pages.
Columns with now hiring, location, openings, and apply. A zip code in Austin, Texas is highlighted with text, remember this.
This is another third-party site that we aggregate. This is the landing page for Gold's Gym. This page has no jobs. We have to navigate through this intermediate page to get to their jobs page.
Pick positions. A list of positions with brief descriptions. Positions are highlighted with text, ag every job.
Nice trick. This is not a jobs page either. We have to get through this page to get to the jobs.
Position detail with highlighted areas.
After navigating through these pages, we get to the job details pages. You can see here some of the important fields that we extract for a job. We have a title, we have a classification of the job as part-time or full-time, we have a job description, and we have an experience requirement, 6 months experience. Notice that there's no company listed here. We in aggregation have to know that when we crawl this page because we can't get it out of the page. There's no location here either, but we can remember it from 2 pages previously where it was listed. A conventional crawler might be able to associate these labels with these feeds, but they wouldn't understand what these labels mean. We know, because we are a domain-specific engine, we know that these are jobs, and those are job fields.
Text, what's in a job? Block of code inside brackets with a URL and job title.
We hit these job details pages, and we extract into a normalized form the content of the job. Each job has a permalink URL that we can send our job seekers to. There's a title, there's a company, various other fields that you might expect to need when serving jobs to job seekers.
Non-English job description.
This job is Greek to me, but it's great for Greek job seekers. The aggregation can extract jobs just as well from this site as from an English site, so we can give Greek jobs to Greek job seekers, and Japanese jobs to Japanese job seekers. Our mission in aggregation is to get all the jobs all around the world.
How we build products.
That's the aggregation problem. Now we need to build something to solve it. At Indeed, our products have 4 key characteristics. They are simple, fast, comprehensive, and relevant. Simple in aggregation. Aggregation is a simple problem. Get all the jobs. Solving it is really, really hard, but we should still strive to have a simple solution. Fast. We need to discover jobs soon after they're posted on the website. Then we need to aggregate these jobs and deliver them to our job seekers within minutes.
Web page shows job search results for Java. 7 minutes ago highlighted.
About 10% of our job seekers, when they interact with the search results page, they sort by date, which shows the newest jobs first. On this page, you'll see that our newest job is 7 minutes old, so we're doing all right in the speed department. On our home page, we show links to search results pages where you can limit the results by their age, only showing the newest jobs that we have. 20% of our users choose to use that functionality. Finally, millions of job seekers have signed up to receive daily emails containing only the newest jobs. We have as many people reading these emails as we have visiting our website. In short, fast is critical to us. Speed matters. Every single day, millions of job seekers tell us that speed matters in the features they use and how they use them. In aggregation, what it means to be comprehensive is very simple. Get every job. Not some jobs, not most jobs, every job. Relevance. Relevance is multifaceted in aggregation. We must extract semantic data with high fidelity. Software engineer is the title, and Austin, Texas is the location, not the other way around. Relevance means that this job is still available. Job seekers are not interested in a position that has already been filled. Then we need to ignore non-jobs. A page might not be an actual job, it may merely resemble a job, but be an ad for an online degree. We try very hard to get every job and get as much information about these jobs as we can, but we can't overdo it and pull in things that resemble jobs without actually being jobs.
This is a hard problem.
This is a really hard problem to solve. A site may have high-quality jobs for our job seekers, but perhaps their engineering is not as of high quality. We may get many jobs on Monday, but on Tuesday we get nothing but 404s or 500 errors. Sites are redesigned often, substantially changing their layout. Something that used to have a location may turn into the title, and the company name may disappear entirely. We need to be able to detect this and fix this. These days, many sites use JavaScript, not just pure HTML. We have to do additional HTTP requests to fetch this JavaScript and then execute the JavaScript to fully populate the details of a job. Finally, many jobs have missing or bad information. You'll recall with the Gold's Gym job that the job pages didn't state the company, and the location was shown 2 pages previously. We have to know the company to fill in that missing blank, or perhaps there's a misspelling, like the recruiter didn't know how to spell Tallahassee. We still want to aggregate that job to a correct location, because it could still be a quality job. This is a hard problem.
Text, big N, makes it even harder.
Now you take this hard problem and you solve it 38 million times a day. That is aggregation. We have to do this whole thing, do it in minutes, and deliver it to 100 million job seekers. So you look at this problem, and let's consider this straightforward strawman architecture.
Diagram shows job sites that lead to engines in either Datacenter A or Datacenter B. Engines lead to one cylinder labeled MySQL, primary datacenter.
We have many aggregation engines interacting with job sites to extract the jobs from them. We run them in multiple data centers, so we have better stability in case of a data center failover event. These ag engines then write these jobs to the MySQL database. Search will read from that database to write the jobs index. I actually lied. This isn't a strawman architecture. This is the architecture that sustained Indeed for the first 6 years.
Limitations.
There are some clear limitations here, though. The number of database connections that you see here is going to scale with the number of aggregation engines. This imposes a limit on the total number of aggregation engines we have, which imposes a limit on the number of jobs we can get and how fast we can get them. We also scale the number of concurrent writers with the number of aggregation engines. That has a similar effect on our scalability. These cross data center connections have latency of about 30 to 60 milliseconds on average. This latency applies to every single database operation. Higher latency means lower throughput, which limits our ability to get all the jobs fast. We could increase the number of threads and engines that we have, but that'll just make the previously described problems worse.
Failure points. On diagram, one engine is crossed out, with the connection to MySQL also crossed out.
An engine could die, but if we lose that engine, the overall system can continue. However, if we lose the network, all work is stopped. If we lose the MySQL database, all work is stopped. This architecture won't do the job.
Scaling patterns.
So we've dealt with these problems before. At Indeed, we have some experience with scaling and resilience. What has worked for us so far?
Diagram with 2 dotted line boxes, remote data center and primary data center. In remote data center, 3 engines with arrowed lines that reach to job write service in primary data center. MySQL connected by an arrow to job write service.
We've applied service-oriented architectures to many of our systems with great effect. This uses our homegrown boxcar infrastructure, which you can read about on our blog using the link shown here.
go.indeed.com/boxcar.
This has greatly improved performance, resilience, and scalability as we've grown. Let's try that here. Here we show our aggregation engines sending their results to a job write service instead of directly to the database. What does that look like in practice?
A diagram with client, service, and database. Arrows move cyclically.
This is our standard service interaction. The client sends a request to the service and waits. The service sends a request to the database and waits. The database works and then returns its results to the service, which then does the rest of its work and returns its results to the client. We don't actually need that. This is what our interaction needs. Send the request along, get acknowledgement from the server, and then continue. We don't need to wait for the service to finish its database interaction. We can decouple that interaction between the service and the database from the interaction between the client and the service in order to make our architecture more efficient. So we modify the service to return immediately after getting the request instead of waiting for the database. Does this do what we want? Well, we have lots of workers that can fetch a lot of jobs. They're sending lots of results across long network links. The jobs need to get processed fast. Maybe this architecture can do all of that, but can it do it reliably? I don't think this is going to meet our reliability goals.
Engine failure diagram, with one engine crossed out in red.
We have the same problem. If the engine crashes, we lose whatever work it has in flight. That's a non-critical system failure because we lose that engine's work, but the other engines can continue.
Diagram, engine failure fix, buffer to disk. Each engine box shares a space with cylindrical disks.
We can partially remedy that by applying a disk. These engines will buffer their work to the local disk, and then if they crash, when they recover, they can at least send that work. Whatever it was in RAM was lost, but what's on disk we can retrieve.
Network failure. Red X on arrows which connect engines and job write service.
What if the network goes away? Well, we can solve the same solution. We buffer our writes to the disk. We'll also add a retry queue for when the network returns to send those writes back across the network. We don't have to worry about redundant writes in this case because our job writes are idempotent. If we write the same job twice, it may be wasteful, but it's not incorrect.
Job write service crossed out.
What if the job write service fails? Well, buffering to the disk. We've already solved that problem. That will work around any planned or unplanned downtime in the job write service.
2 more job write service boxes appear.
We can also add redundancy. We can add additional job write service instances so that if one of them goes down, the clients can communicate with one of the other instances.
MySQL crossed out.
The database may fail. With no database, those job write service requests have nowhere to go, so all work is stopped, potentially lost. We can add disk buffers and retry queues to the service as well. If you put that all together, you get something like this.
A diagram which has 3 engines with disks all connected to 3 job write services with disks, which leads to 1 MySQL.
This is an architecture that could meet our needs. We could build this, but it seems like it's a general solution to a general problem. Maybe somebody else has already built this. Surprise! We should use a message queue. Cameron Davison, a developer on our aggregation team, will tell you more about that.
Mr. Davison stands and takes the place of Mr. Gangatirkar.
Thank you, Kathan. Hi, I'm Cameron Davison. I'm a software engineer on the aggregation team. And as Kathan said, we had the idea that message queues would make it easier and more reliable for us to write to the job write service. But in aggregation, what are our requirements in order to be able to do a good job, to have the message queue do a good job?
Aggregation requirements.
Firstly, we talk about making sure that we don't lose any jobs. We want them to be durable. We want them written to disk because we never want to lose a job that it's potentially a job for a job seeker. Also, aggregation is in multiple data centers. So we need a message queue system that will be able to handle writes from multiple data centers over high latency highly unreliable connections. Also, aggregation is processing 38 million jobs a day. Our job size is about 2 kilobytes, so that means that we're processing 76 gigabytes of data a day. So we need a message queue that can handle that load. At the time that we were looking into message queues, our writes were at peaks of 350 jobs per second. So to give us some extra room to scale and make sure that we could continue writing for growth in the future, we wanted to target a message queue that could provide 1,000 messages per second. Also, our engines are written in multiple programming languages. So it's important for us to be able to find some client that is programming language agnostic and be able to communicate with the message queue.
Text selection.
So we started looking at different message queues. We wanted to see what's available, what kinds of things can solve this problem.
5 company logos, including ActiveMQ and RabbitMQ.
We found that lots of message queues were available, but we needed to narrow this list down some. In particular, to us, we wanted to make sure that our engines could continue writing to this message queue all the time. We needed something that was highly available. Turns out ZeroMQ is something more of an architecture for writing from client to server, not a message queue system in itself, so that didn't work for our use cases. Also, here at Indeed, we always like to try to find free products. If it's free and it performs well, then that's going to save us money in the future. A dollar spent today is going to be double that and quadruple that in the future as we grow and grow in the company. So at that point, we were able to throw out WebSphere MQ because it was a paid product from IBM. Also, our aggregation engines are hosted ourselves, and we're running those engines ourselves, and we wanted some thing that would be able to write locally and write our jobs to that same infrastructure that we already set up. So we didn't want to use any of the cloud messaging services. That left us with 2 products, ActiveMQ and RabbitMQ, to start playing around with and looking at and making sure that they could handle the performance that we need. Because we do have a high amount of jobs that we're writing, and so we need something that's highly performant. We started sending messages through both RabbitMQ and ActiveMQ to see what kind of message rates they had. And it turns out that we were able to send 1,000 messages per second through RabbitMQ, persisting those messages to disk. And in the configuration that we picked for ActiveMQ, we're only able to see 100 messages going through ActiveMQ and being persisted to disk. This was an order of magnitude difference. So it was clear that the RabbitMQ was simple, easy to get set up and started with, and it was already meeting our target messages per second. So we wanted to continue moving in that direction and see if it could actually meet our performance standards. Also, RabbitMQ uses the Advanced Message Queuing Protocol.
AMQP.
This is an open protocol that is contributed to by multiple companies. It's also a wire protocol, which makes it very easy to write clients for this. Actually, there are lots of existing clients already available that speak through AMQP, and this helps in some of in ag, given that we have multiple engines running in different languages.
Concepts.
So just to get started with some of the concepts of RabbitMQ that I can go through so that I can set up some of the test case that we did to make sure that RabbitMQ would work in our system.
Confirmation and ACK. Diagram shows MQ at top with arrows that lead to and from 2 boxes, producer and consumer.
First, confirmation and acknowledgement. When a publisher publishes to a message queue, it publishes the message to the message queue, and then once the message queue has properly persisted that to disk, then it will actually confirm that message back to the producer. At that point, the producer knows that the message queue has the message, and it can forget about the message and move on to processing the next task. Also, when you're consuming from a message queue, you can get your messages either by polling from the message queue or by having the message queue push the messages to you by subscribing to the queue. We opted to use the subscription-based push method because we wanted to get these messages through our systems as quick as possible with as low as latency as possible. Once the producer finishes working on that message, then it can give that acknowledgement back to the RabbitMQ, and it knows that it can forget about that message.
2 diagrams. 1, at least once. 2, at most once. In at least once, an ACK arrow leads from consumer to MQ. In at most once, auto ACK between MQ and consumer.
In particular, Kathan talked about the fact that we're able to replay messages such as our jobs because they're idempotent. We have all of the content of the job every single time, and we can just rewrite the entire job back to the database. This makes it possible for us to send the message multiple times from RabbitMQ, and then once we actually process it successfully, only then send back the ACK. That allows us never to miss any messages in that time frame. Also, RabbitMQ can be configured to only send the message at most once. The only difference between this is that every time it sends the message, it'll automatically acknowledge the message and then therefore never give it to another consumer. RabbitMQ also allows for asynchronous confirmations. A producer produces messages sequentially and continues producing messages waiting for a confirmation to come back from Rabbit. When that confirmation comes back, it not only confirms that message, but all messages prior to that message. This allows the producer to continue producing messages and cuts down on the number of confirmations that Rabbit actually has to respond back with.
Persistent. Green box travels from producer to MQ then to consumer.
If you want your messages to be durable and written to disk, then you can set your messages to be persistent. And then when the producer produces the message to Rabbit, even if Rabbit were to go offline and we restarted it, when we restarted it, it would have the message again and be able to give that message to the consumer.
Clustering.
We can also configure RabbitMQ to be in a cluster where you have producer producing to a master that's then writing that same message to the slave synchronously and waiting for that slave to give back its confirmation before actually confirming the message back to the producer. This cuts down on the throughput, but gives us a little higher reliability because we've actually been able to write the message on two different servers during that process. And in this scenario, if the master or the slave were to go down, the master would be able to continue processing messages. It's not going to wait for the slave to become available again.
Text testing.
So now that I've introduced some of those concepts, what did we actually do to test that RabbitMQ would work in our real scenario? We built a test that would actually send millions of 2 kilobyte job messages. We had 20 producers, 20 consumers. They were sending a combined 1,000 messages a second. And during that whole process, we were simulating multiple failures to make sure that Rabbit didn't lose any of the messages and that every message that got produced would actually get consumed by the consumer.
Test consistency. 3 colored boxes starts at producers. 2 cylindrical RabbitMQs in the middle, master and slave. Consumers at far right.
In this diagram, I've labeled the messages with colored boxes. We have a lot of producers producing to a cluster of rabbits, and then a lot of consumers consuming from that cluster. As the producer produces the red message, it gets to the cluster and is on both the master and the slave. Then the consumer can consume it as we continually produce messages into the cluster. But in the middle of this test, we killed the master server, and the slave automatically became the master so that we could continue processing and producing messages, and the consumer continues to consume until it's consumed all the messages. And at that point, we even turn the slave back on, and now we have our same clustering configuration, except for just with the master and slave switched. This test knew every message that was going to be produced, and the consumer knew every message that was going to be produced. So we were able to verify that all of the messages got through the entire system appropriately. There's a lot of failure scenarios that could have happened with the cluster, and I went through just one of them. So let's zoom in on that cluster a little bit and just talk specifically about it. If we have a cluster with a master and a slave and one message on it, we can produce a message to that cluster again, and now we have both the red and yellow in the cluster. And if the master were to go away, like the example that I just showed, the slave would become the master, and we could consume the red message off of the master. At this point, you could see that the old slave, or the old master, has the red and yellow messages still because they were persisted to disk. But when we turn that slave back on and it reconnects to the cluster, it doesn't know what the state the master was in, so it forgets all of the messages that were on disk. At this point, if we continue producing messages to the cluster, the slave will get all the new messages, but will not read the messages that were on the master already. We would consider the slave at this point to be unsynchronized, but it will become synchronized as soon as that yellow message gets consumed off of the master. At that point, the slave would know that its oldest message was as old as the master's oldest message. If we continue producing messages through this cluster, they'll make it through the entire process and get to the consumer in the end. But let's go back to that unsynchronized slave. What happens at this point if we shut down the master? If we shut down the master at this point, the slave becomes the master, and it didn't have the yellow message, so the yellow message actually would get lost. So it is very important that we do not shut down the master while we still have unsynchronized slaves and consume all of the messages off the master. You can check to see if the slaves are unsynchronized by looking at the web management console in RabbitMQ, as well as running a console command line utilities to see if it's still unsynchronized. If we're in the middle of producing lots of messages and we need to shut down the cluster at any point, it's always safest to continually shut down the master. If we shut down the master, the slave becomes the master. And then if we shut down the master again, at this point there's no nodes running in the server. And if we turn that master back on, it's not going to have another master read from, so it doesn't need to forget its messages. And since they're persisted to disk, it will reread them back up off disk. And then we can continue consuming from it and get those messages off of the cluster. And once the messages are all off of the cluster from the master, if we turn the slave back on, it'll become a synchronized slave again, and we can continue producing messages to it. Throughout this process, we kept track of the throughput that we got through each step. And if we're not persisting messages to disk, we're able to write these 2 kilobyte job messages at about 16,000 messages per second. This is well above our target 1,000 messages per second, but we want to have them be a little bit more durable. It's actually 30 megabytes per second, which is an incredible amount of data going through RabbitMQ at this point. When we turn on persistence and start writing these messages to disk, things got a lot slower, but it's still about 2,700 messages per second, and that's still above our target 1,000 messages per second. When we turn on the cluster and have these messages persisted on two different servers, we're still seeing, we saw a little bit more a loss in throughput, but we're still able to produce messages at 1,200 messages a second, which is still above our target 1,000 messages a second. So we're feeling pretty good that RabbitMQ doesn't lose messages and is above our target of 1,000 messages a second. So how do we put this into our system? Kathan talked about the fact that we have these unreliable connections between the remote data center and the primary data center. Let's add RabbitMQ to this. Well, we don't know exactly where we want to put it yet, but let's also take MySQL out of this picture because it'll stay around, but we're going to just concentrate on engines, RabbitMQ, and the job write service.
On diagram, RabbitMQ receives arrows from engines in remote DC, in primary DC, RabbitMQ with an arrow to job write service.
At this point, we see that the job write service is actually able to read from a local Rabbit with sub-millisecond response time over a very reliable connection. So things are looking good from its point of view. But the engines are still writing over this high latency, unreliable connection between data centers. So they're not going to be able to continue processing work if that were to go down. So maybe we can move the RabbitMQ over near the engines.
RabbitMQ moves to remote DC.
At this point, the engines are able to write reliably to a low latency RabbitMQ, but now the job write service is reading over that high latency connection. And if in the event of a network partition, now the job write service is unable to do any more work and is unable to continue processing jobs.
Text, Rabbit can talk to Rabbit.
Turns out Rabbit can also talk to itself. This is different than clustering rabbits, but in essence, with the Rabbit shovel plugin, one rabbit is able to consume from a local rabbit and then produce those messages to another rabbit. This is nice because our producer can send the message to rabbit 1 and get the confirmation back from that rabbit before that message has even reached the next rabbit and way before the consumer has the message.
A diagram shows 3 RabbitMQs next to 3 engines.
This allows us to put rabbits in both the remote data center and the primary data center. So we get the best of both worlds. The engines write locally to a RabbitMQ, and then the job write service reads locally from a RabbitMQ. In this diagram, though, we still only have one rabbit in the primary data center, so we can introduce clustering, and that gives us higher availability of that rabbit by having multiple copies of it running, as well as giving us the more reliability of having those messages on 2 different servers. When you're consuming from a queue in RabbitMQ, you consume sequentially from messages sequentially from that queue as the consumer becomes available. If we have multiple job write services, each one would get an individual job, which allows us to also work on those jobs in parallel. With this, we can add another job write service as well and make that not a single point of failure by having multiple job write services. We can also continue to scale our remote data centers by adding more of those because the connections through the Rabbit cluster are very lightweight.
Message flow.
So in this new infrastructure, how do messages flow in the event of a network partition? We were talking about that before, so let's go into that a little bit.
Diagram. 3 vertical engines point to 3 vertical RabbitMQs. Arrows lead from RabbitMQs to primary DC RabbitMQs, which are shaded half green. In this diagram, the green is representing messages. The engines are writing to a local RabbitMQ, which has no messages in it, though they've all been shoveled over to the cluster. The cluster has a small amount of messages that are buffered up, waiting to be processed by the job write service. In the event of a network partition, then the engines can continue doing work. They can continue writing to their local RabbitMQ, and the job write service can continue reading from the cluster and reading the buffered writes that were already in the cluster. The cluster would quickly go away, but the engines and job write service would continue working until the network partition came back and we were able to get back into our steady state, where the engines have no messages or little to no messages, and the cluster has a small amount of messages that are buffered up. Line graph titled Jobs per Minute.
This graph is the number of jobs per minute that we process at Indeed. It's showing a month span right before we moved to RabbitMQ to right after we moved to RabbitMQ.
Lines take sharp incline in middle of graph.
You can kind of see right in the middle where we moved over to RabbitMQ. We're seeing double of throughput, even higher peaks, being able to process more jobs per minute. It's kind of hard to tell exactly how much this helped us, but if we zoom in on one specific site, we get a lot of good information. This site, before we were using RabbitMQ, we were only able to process 220,000 jobs in 6 hours.
611 jobs per minute.
But after we moved to RabbitMQ and took advantage of writing locally to a message queue as well as parallelizing the writes, we were able to process 251,000 jobs in 20 minutes. We're seeing a lot of improvement.
Horizontal scale.
Also, RabbitMQ allows us to scale horizontally. As I talked about with the job right service, adding more of them actually will consume in a load balanced fashion from the consumer. With just changing some configuration of the shovel, we can add another shovel to shovel this load balance to another RabbitMQ cluster. So if we added another one, we could double our throughput, move further away from that red bar, and we could even add another one and triple our throughput, moving even further away from that target of 1,000 messages per second. That's good because today we're actually at 1,000 messages per second. But while we've been working to make things better at Indeed and get jobs faster and more reliably, RabbitMQ's community has also been working on making their product better. And for free, we can upgrade to the latest version of RabbitMQ, where they've put a lot of work into writing persistently to a cluster. And in the next version of RabbitMQ, RabbitMQ 3, some of our testing has shown that we can write about 2,400 messages a second of our 2 kilobyte job messages. And this is just for free with a software upgrade.
RabbitMQ configuration.
Just to recap, we're using confirmation to be able to write the messages to Rabbit and then get the confirmation back and know that Rabbit has gotten the message successfully. And then we can forget about the job and move on to the next job. We're using persistent messages to persist those messages to disk and in a durable fashion. And we're using the shoveling plugin to be able to shovel things across from multiple data centers to our primary cluster. And the primary data center is using the mirrored queues in a cluster where all of the messages are written to disk in both the master and the slave. And that gives us higher reliability, having the messages in 2 different servers, as well as higher availability by being able to restart or stop one of the rabbits but continue doing processing throughout that. At this point, I'd like to invite Keithan back up to talk a little bit about some other use cases of Rabbit in the company that we found it successful.
Mr. Davison passes projection remote back to Mr. Gangatirkar.
Thank you, Cameron. So Cameron pioneered the application of RabbitMQ in our aggregation infrastructure. And after some time spent with it, our experience was very positive. It had good performance, it was reliable, and it was easy to work with. We started to look at other products and other problems that we needed to solve to see if Rabbit could help us there. You may recall the aggregation viewer that we had on the screen at the beginning. If you missed it, there we go. Sorry, I'm not good with computers.
Indeed. Ag got a job. Red dots on a globe, job titles and descriptions.
So this is a live view of what our aggregation engines are doing. Basically, seconds ago, they have interacted with these sites around the world and extracted jobs from them. And you can see some of those flashing by.
Aggregation viewer architecture. Almost real-time, exclusive queue, transient messages. A diagram moves in the order of jobs, Ag Jobs RabbitMQ Cluster, Shovel, Ag Viewer RabbitMQ, Ag Viewer, HTTP, Browser.
Now, this viewer, it's a fun thing, it's a neat thing, it's a cool thing, it's not a business critical thing. It's plugged into our real production RabbitMQ cluster that's processing jobs that Cameron just spoke about. However, we're using the same shovel that Cameron described earlier to disconnect at one level of indirection so that nothing that this viewer application can possibly do could affect the production cluster. RabbitMQ has very lightweight queues and very lightweight connections, so there's almost no impact on the performance cluster by running this application. One thing that the shovel can do is transform the messages as it shovels. And so those messages on the production cluster are persistent, but when they get shoveled over to the Ag Viewer RabbitMQ instance, they're no longer persistent. So in case of a crash, they get lost. This is acceptable because this is a real-time viewer. We don't care about jobs that went through 30 seconds ago or 30 minutes ago. We just care about what's happening right now in the moment. For the same reason, we use a feature of RabbitMQ called exclusive queues. That means that this queue is bound to a single client. If that client disappears, there's no queue, and any messages destined for that queue just disappear. That way, we are processing and taking the overhead of these messages if there's a client, but if there's no client, those messages just go to dev null. We also applied RabbitMQ to our resume product for the managing of billing of contacts. So a lot of you work at software companies, and Maybe you're looking for a VP of engineering to help run your organization.
Indeed resume for Douglas Gray.
This fellow looks like a promising candidate, so maybe you want to contact him to discuss this exciting opportunity. One of the ways we make money off a resume is by pay per contact. So if you're a recruiter, we want to charge you for this contact and then limit you to the number of contacts allowed by your budget.
Resume contacts billing, original path. Diagram with Pacific Ocean in middle, Asia DC on left and US DC on right. Resume search in Asia leads to log repo in US, which leads to MySQL cylinder.
We were already logging these contact events and populating the database from them. This was using our log repository storage system, which you can read about on our blog at the link shown here.
go.indeed.com/logrepo.
These messages were transmitted reliably, but they had a 17 to 35-minute latency. We wanted to reduce this latency because we wanted to ensure that employers did not contact job seekers beyond their budget.
RabbitMQ cylinders appear in both Asia and US DCs.
We added a new path for this via RabbitMQ. This updated the database within seconds.
Company page edits, user-contributed content about companies.
We also had another use case of company pages. We have company pages where job seekers can learn about companies to determine if they're interested in working there. The owners of these pages should have a fast, reliable editing experience. Now, as mentioned before, Indeed is an international company, and we have company pages for companies from around the world, and we have a data center presence to match that. One critical difference between company pages and aggregation is that company pages need to read the data back again, whereas Ag is writing and then moving on. The architecture is trivial when you're operating from a single data center.
Single data center diagram. Browser connected to web server, which is connected to MySQL.
You just read and write from your database. It's that simple. When you have a distributed presence, it's not that simple.
Company page serving. Asia data center. Browser and LSM tree connect to web server, which is interconnected to Memcached.
This is what we did instead. In each of our remote data centers, we serve company information using a Memcached and an LSM tree. The LSM tree is an Indeed-developed, high-performance key-value store that we described in our last Tech Talk. You can see the video and the slides from that Tech Talk at the blog link there.
go.indeed.com/LSM tree.
The browser will request a page from the web server. The web server will then request the information for that company from both the LSM tree and the Memcached. Whichever one supplies it with the newest data, it selects those data and renders them and returns them to the browser.
Diagram expands with oceans that appear between Asia, US and EU. Web server from Asia points to Asia's RabbitMQ, which points to US's RabbitMQ, then US's MySQL, etc. in EU data center.
When an employer updates their company information, we do two things. First, we send the update off to our primary database in our primary data center via RabbitMQ. That's via the local RabbitMQ, which is then shoveled to the remote RabbitMQ, which the messages are then written to the database. We also write that update to the local Memcached so it can be immediately available to local clients.
LSM tree builder in primary US data center extends to LSM trees in both Asia and EU data centers.
For the read side of this, we compile these database contents into an LSM tree. This LSM tree is then copied to all of our remote data centers as the complete store of record for company information. It's not just this Asian data center, but there's also a similar EU data center and other data centers around the world that all need to have a complete copy of this company information. Again, had we been using a single data center, we would have simply read and written directly to the database. These long connections across the ocean with their hundreds of milliseconds of latency made that system impractical. Sorry, that solution, whatever.
Other applications. Company pages. U.S. Air Force company page with photos.
We've also applied RabbitMQ to a number of products beyond these. Company photo uploads, where a user can upload a photograph of their employer, their office, or some of their products, or what have you. Those are all transmitted by RabbitMQ.
Indeed apply. Austin, Texas cosmetologist job with description. Apply now button.
Job applications that are submitted via our Indeed Apply product, those are transmitted via RabbitMQ.
Indeed for employers. List of jobs with numbers of views and candidates.
We have a product for employers to manage their job postings. Applications to those jobs are transferred using RabbitMQ. And there are actually quite a few more, but I've gone on long enough.
Recap, the jobs must flow.
To recap, for over 6 years, the obvious architecture for aggregation served us very well. In 2011, however, our growth started to approach its limits. We analyzed our existing architecture and we projected our future needs. From that process, we derived an architecture that would serve us for years to come. Essential to this architecture is the queuing system of RabbitMQ. It has given us what we need in this system. We have durability from its writing to disk efficiently. We have high throughput that more than meets our needs, especially with RabbitMQ3. We have low latency with all of our direct actors that talk to RabbitMQ. The shoveling system effectively covers the cross data center latency. We have partition tolerance. In case of a network failure, we can continue to do useful work on both sides of the partition for a time. And we make efficient use of our database. We don't have this ever-growing number of concurrent writers or database connections that could limit our scaling in the future. And it helps us minimize the number of points of failure we have, ensuring that we can help our job seekers find the right job.
Q&A.
So that's how we've used RabbitMQ here, primarily in aggregation. I'd like to open the floor up for questions.
Text, engineering.indeed.com. At Indeed Eng. Tech Talks on the fourth Wednesday of every month.